Hello, I'm Chris Barratt. I'm the CTO of Insight SiP, which is a company in the south of France where we design and manufacture ultra miniature radio modules. Typically, we have a range of BLE modules on an 8x8 by 1mm size platform that contain everything you need to do BLE, including the processor, the radio, and the antenna. And we also have a range of other modules with ultra-wideband and LoRa, both including BLE as well, and both including all the antennas. Today, I'm going to talk to you about a particular aspect of these devices, and in particular, anything to do with IoT and wireless devices related to security. Security is quite a big issue for IoT and wireless devices. So the agenda for today's talk is I'm going to start off by giving a brief introduction to IoT and wireless devices. Then I'm going to talk to you about security risks and consequences of those risks that can occur. I'm going to give you a little bit of information about typical attacks that can happen and attacks that have been attempted on devices in the IoT world. A little bit about keys, signatures, and authentication, and finally some ways in which you can protect your devices using hardware that is available today. So I'll start off by talking about IoT and wireless devices, and I'm going to compare what happens in terms of security in the PC phone world compared to the IoT device world. So if we start off and we look at the PC or the phone world, you have extremely powerful processors, and the hardware has a lot of aspects to help protect you. In a phone, you have a SIM card, which is more or less as strong as a bank card in terms of protecting your identity and making sure it's you that's using the phone and communicating. You may have other biometric sensors in either the PC or in the phone. You have a lot of pre-installed trusted certificates in PCs and phones that allow you to connect with some degree of security to the internet. And you obviously have firewalls, virus checkers, and lots of everything else to help make the connection between you and the rest of the world as safe as possible. So you could say in the PC phone world, you have security straight out of the box, up to some sort of reasonable level, at least. If you now look at the IoT device, typically an IoT device is quite small. It has a small processor, and typically the program is put onto it in bare metal, so there's no operating system. It has limited or no security in some cases in terms of hardware. The memory capacity is many orders of magnitude less than the PC, and there are no pre-installed security services on the IoT device. So security, in terms of preventing hacking and attacks in the IoT device world, is basically do it yourself. Again, another aspect we should look at is the difference between a wired communication and a wireless communication. If you have a wired communication, you have physical connections between every part of the system. And putting a man in the middle to try and either spoof you or steal your data or interfere with your data is fairly complicated because you have to have physical access to equipment and cables. On the other hand, in the wireless world, the transmission from end to end is at least in part over the air. And anything that is being transmitted by waves over the air is potentially open to anybody to look at, to steal, and to get their hands on. And this makes attack possible from a distance. You don't even have to see the person you're attacking, and obviously more open to interception. So the rest of the talk is going to focus on risks that happen to wireless IoT devices and how you can prevent those risks causing you any harm. So with a wireless IoT device, what is the problem? Well, first of all, I've already indicated that the system architecture is rather vulnerable because it's quite small and doesn't have a lot of overhead. Very little protection is provided out of the box in a typical IoT processor or in an IoT system. As I said previously, the devices have rather severely limited capability. IoT systems also have large numbers of nodes, so you can potentially get into the system at a number of different places in the system. And they're often highly distributed, so there are many different places you can do it. So the question is, what can you do? And I would have said up to a few years ago, not very much. I'm now going to talk a little bit about security risks and potential consequences of those security risks that you might find in wireless IoT devices. So the first thing to realize is that security isn't something that you can bolt on to an IoT device once you've finished the development, the design of the hardware and the firmware and the overall system. So it's important to start off and decide what level of security you need. And you start off by building a system architecture, in other words, hardware and firmware, that will create the level of security that you think you need in your system. And this will influence a number of different choices you make during your design process. It will influence the choice of processor or BLE chip or Wi-Fi chip that you may choose. It will influence what peripherals you consider necessary in the device. And it will also have an impact on the overall memory requirements of the processor in the device, depending on how you want to protect yourself. And so you need to do a functional design, and you also need to think about what happens to the data when it goes from the wireless node to the server at the end of the world. So you need to start off by thinking about your system and look at potential threats and risks that might happen. Once you've decided what you think the threats or risks to your system might be, you should look at possible lines of attack and consequences of the attack. Consequences of attack can be many. It could just be nuisance. It could be that your service doesn't get through, or your server that you're using gets locked out because of a denial of service. It could be that your system doesn't work anymore, so you have a reputational issue. If you start delivering temperature sensors that don't work because somebody's hacking your system, then it's not very good for your reputation. It may not be dramatic, but it's not good for your reputation. There may be financial implications if you're transmitting payment details or other things over the internet from your device. There may be privacy implications. You may be tracking people that you shouldn't be tracking. You may want to try and anonymize things to prevent that. And in the worst case, it can be life-threatening. And I'm going to show you a couple of examples of people who have shown that with certain medical devices, it's possible to attack them. And given the type of device, this could be something that leads to a fatal conclusion. And so I'm going to talk now just about some attacks that have actually been documented in the past. And they all refer to insulin pumps and glucose monitoring. If you have an automated insulin pump that is controlled by some wireless system, then you rely on the fact that you have probably a closed loop system in which you have a glucose monitor that's monitoring the level of your glucose, and then you pump insulin to compensate so you have the right level of insulin in your blood. This is a YouTube you can go and look at afterwards, but what happens is that this researcher in 2011 showed how that you could hack a Medtronic insulin pump and you could kill yourself. And since then, other manufacturers of devices, similar devices, have been shown to have pretty severe vulnerabilities. So both insulin pumps and pacemakers have been attacked. In one case with a pacemaker, the attack was to try and short the price of shares in the company that was making the pacemaker. So you can see it's not just a fatality, it could also be financial. So how do you hack a medical device? This is a different device. It's a MiniMed pump from a different manufacturer. They took advantage in this case of the pump's communications, which are not encrypted in this case. And the methodology was to reverse engineer the encoding and the fidelity checks that were meant to protect the signal. And then they used open source software to program a radio that looks like the legitimate MiniMed remote, sends commands that the pumps will trust and execute. And once you've made the contact, you can do anything you like with the pump. So that's not a particularly good thing to have. And again, this is another example with a Medtronic insulin pump. Another guy, he managed to do the same thing basically. And I'd like to indicate that the results of this sort of hacking of a simple IoT device, wireless IoT device, could actually be fatal. So we've seen that you may need security in your wireless IoT system, but you have to consider the cost of any implementation. Security doesn't come free. There are certainly potential costs for any added security that you put into your system. These can include taking it a lot longer to get your arms around things that are necessary to do the design. So your design cycle spirals out of control. It will probably mean that you have to consider not buying the cheapest device that's out there on the market, but you need to go upmarket a bit with your choice. So your end node will become more expensive. The usability of your system, in other words, how you connect to it, how you manage it, becomes more complicated because you need to put certificates everywhere, and you need to make sure that if you put certificates everywhere, they are securely put there. So it's not something you can do just anywhere. So bear in mind that depending on what level of security you think you need and what level of security you actually put into your system, there is some sort of a trade-off with cost and performance. Again, performance is affected because you're probably doing more processing, and therefore you're having delays in the way that the signals get through, and you may not have the same throughput that you had prior to having added security to your system. So in this slide, you have to bear in mind that any added security is going to add costs. So you need to balance how much extra security you need with the risks that are associated with adding that extra, with not adding that extra cost. But if you're doing a careful design, you should make conscious, positive decisions so you know why you've done what you've done. So I'm now going to talk about different types of attack and what you might be able to do against each of those attacks. Some of these are not particularly prevalent, but I'll still talk about all the different types of attack you might have. Well, the first type of attack is you might have somebody who has actual physical access to your device and may want to put a piece of sleeper firmware in there that could activate and then cause your device to become a zombie, or to corrupt your device, or to send information you don't want to send to people you don't want to send it to. It's quite difficult to protect against, but it's not often a real problem, provided you are in control of your hardware. You could consider using memory that you can't change. You could consider adding a SIM card or some sort of integrated secure module where you keep anything that's secret. And you could try and prevent probing by either putting it in a steel case or by other techniques in the components themselves. However, this sort of attack is fairly rare for small devices, and it's unrealistic to protect physically your devices in most cases. The next level of attack is what you might consider as being the most important thing to protect against. It's what I would call the sniffing in between the transmitter and the receiver along the line in the wireless network. In fact, it's actually fairly limited risk. There is a risk, but it's fairly limited. Most wireless links have some sort of encryption. It's not always turned on. That could be a decision you make to improve your security as you switch the encryption on. Most of wireless BLE Wi-Fi devices, you can switch on at least 128-bit AES encryption. It's probably good enough for most purposes, but the risks actually lie elsewhere. Obviously, activity is easy to monitor by wireless looping, but actually getting at the information may be not quite so easy as that. However, some of the commonest weaknesses for wireless devices are during the initial connection or the commissioning of the device. When you add a device to a system, you typically pair it in such a way that you know you're talking to the rest of the system. And one reason it might be weak is because you do that in the over the air in an open manner when people can sniff and realize what the pairing has gone on. Then you're no longer paired securely. You could be using default keys or passwords. You all know Wi-Fi routers use admin, and the password is probably admin. So that's something that has to be avoided. You can also listen in to the pairing and the commissioning, and then you can have a man in the middle. So you should certainly consider, in terms of pairing as a key item in your security watch, you should consider putting codes in such a way that it's done by hand, or if it's done over the air, it's using a different physical system, hopefully with proximity, using NFC or potentially ultra wideband. And so that is probably the most important part of the whole system, is making sure that you have a correct way of entering any codes, keywords, and passwords, and secure information. Of course, man in the middle is a common issue as well. The individual link might be secure, but as your data is going from your IoT device through maybe a phone, through maybe a GSM or a 3G, 4G, 5G network, and then over some fiber, and then eventually to some cloud-based server, there's a whole range of places where people might be listening in and trying to get at you. And there are many opportunities in this long pathway for people to get in and listen in, or try and change things that are going on that you want to happen, and take control of your device. And not all of these places are under complete user control. So the only way of really preventing man-in-the-middle type of attacks through the whole network is to use what we call here end-to-end authentication and encryption. What this means is that any data you send is securely encrypted at your end, and any data that you receive is also securely sent from the server. And then going through all the intermediate networks, nobody who doesn't have the right certificates is able to actually read your data or get at you or spoof you or do anything you don't want them to do with your system. I'm now going to talk very briefly about keys, signatures, and authentication. You may or may not have looked at certificates in your computer, but you'll find there are loads and loads of trusted certificates in your computer. And most of the security related certificates is based on having what we call root of trust, which basically means that if I have a website that I want to protect and I want to put HTTPS on it, I pay a root of trust provider, which is a company that has basically is going to be your trusted element in the whole system. I'm going to pay him, and he's going to make sure that my certificate has a bit of his certificate in it, so that if I send you some information, you know it's me, because at your end you have this trusted certificate in your computer or in your IoT device. And then, of course, you tend to use public and private keys for this. And the public key for the trusted authority has to be placed on your device securely. This is typically available on any PC, but on an IoT device, it has to be done by hand. And then any data encrypted by a trusted authority using their private key can be validated immediately as being genuine, and then you can act on it. And the same is true for data you send in the other direction. And you can then also, once this flow of data has been authenticated, you can then send any other new keys that you need to send securely. Bear in mind, I said this earlier, but bear in mind that PCs all have a load of root certificates pre-installed. If you want to see, just look in the certificates page of your system. But in IoT, it has to be done by hand. If you ever tried to make a Wi-Fi system with a small Wi-Fi module, you'll realize that it's not a piece of cake, and it involves a lot of heartache from the developer's point of view to make sure that they can put the certificates in a secure fashion so that they can't be cheated on. So, as I said earlier, encryption and authentication both use public and private key systems, the standard encoding, encryption and authentication system that is out there. The public key from the receiver encrypts, and then only the receiver can read using a secure private key, and the other way around. The public key of a sender authenticates. That means that data could only have come from them. And authentication is very often more important than encryption. Just so you know, when you see HTTPS, it means that your computer has validated that the website you're talking to is actually the website you think you're talking to, using a system of trusted root certificates. I'm now going to talk about something which is maybe a little bit closer to home to inside SiP, is what you can do with the hardware side of things to try and secure IoT wireless networks a little bit better than you could do if you don't do anything. So, as I said at the beginning, up until recently, this would apply to all IoT devices. The simplest IoT devices offer nothing. They have bare metal, low spec processors and zero special features. So if you have a simple IoT device, you have to accept that your device could be manipulated. And if you're in an environment where you need security, you need to think about what you should do to improve the security of your device and change the hardware you're using. If you want to add security, you definitely need to be sure that you have devices that have more memory capacity than the simplest Bluetooth Low Energy devices or the simplest Wi-Fi devices. You probably need a main processor or a pair of processors that are significantly faster. For example, you may want to go from an ARM M0 to an M33 or equivalent. You may want to add some place where you can securely store data. And one way is to use an ARM trust zone, which is a portion of the hardware in which it's more difficult to get secure data out of. If you want to go a little bit better, then you can use secure hardware, like in your bank card or in your SIM card, which is also more probing resistant. And once you have one of these two devices, hardware devices, you can then put secrets into them, which will never come out. The only way of getting secrets out is by looking at data that is transiting on the input and output pins. And this is quite difficult with a secure element. It's slightly easier with trust zone, but it's still complicated to get data out. And of course, you may need hardware acceleration for any cryptographic operations. Unfortunately, if you need to add security, it won't come for free. And in life, as you probably realize, as you're probably an engineer, there are going to be trade-offs. More security, more cost; less security, less cost. Less security, more risk of being hacked. I'm going to give you some examples of different levels of security that you may encounter with devices from our catalog. These are all Bluetooth low energy modules. They're all the same size physically. They all include the radio, a microprocessor, and the antenna, so they're totally autonomous. And the different modules are based on different processors. In this case, they're all from Nordic Semi. And the first device, which is was started for us in 2015, is based on a NO52832. It's quite a good device. It has over-the-air encryption, AES data encryption, if you put it on, but it's not easy to store sequence inside, and it's the lowest cost. So it's a good option if you don't need to put a lot of extra security in your system and your data is remaining local. It's quite simple to implement the application. You don't need to be in a secure environment to program, but unfortunately, it could be hacked a little bit more easily than the two other solutions I'm presenting below. The next level of protection is available in the ISP 2053, based on a next generation Nordic device, NRF 5340. It also has AES data encryption, but it also has an ARM trust zone in which you can store secrets. And in the ARM trust zone, once you put a secret into the trust zone, you can't get it out. You can, of course, use the secret to decode, encrypt, or do other things with, but you can't actually copy the secret out again. That's part of the whole idea of having a secure element or a trust zone. The cost relative to the 1507, the 2053, is slightly more expensive. It has the same footprint, more or less, the same size, not quite the same footprint, has the same size. It has a more complex software architecture. It has two processors, so it makes things a little bit more complicated for the software engineer. It needs secure programming techniques to secure the secrets. You may want to do that in a secure environment, not in your just out in the open lab. You may want to do it where nobody else can get at the secrets. However, the secrets are actually stored in what I would call normal hardware, so they are slightly vulnerable to probing. Looking at the noise, for example, on signals that are transiting into and out of the secure section could give you a clue as to what's going on inside the trust zone. The final ultimate choice would be something using a secure element, and we have currently a device that's under development. It's not actually out on the market, it's under development, which is based on a Nordic 52833 BLE device and a TO136 hardware secure element. And adding a hardware secure element gives you the next level of protection against attack, because it's even more difficult to get the security details out of a secure element than out of a trust zone. Why is that the case? The reason that is because the secure element has hardware features built into it that mean that it's more difficult to look at noise, because there have been noise prevention mechanisms and added noise to the signals added to avoid being able to read the security information from the noise that's coming out of the chip. So this would be like your ultimate solution, and it would also be your ultimately expensive solution, more expensive than either the basic 1507 type solution or the 2053 solution. Both 1507 and 2053 are already available on the market. So that's another reason why you might want to go with one of those options as a choice to secure your IoT device based on Bluetooth Low Energy. And there's a little bit to be said also about which cloud service you may want to choose. There are a number of cloud services that you can choose. As you know, there are a large number of industry players that are now offering cloud services. They all have some sort of security built into the infrastructure. And with these platforms, you can potentially implement end-to-end security, with authentication and encryption of your data. So potentially you can set up today a system with an IoT device, quite a small IoT device, that has enough capability to ensure that you can't easily be spoofed, or nobody can easily take control of your system. Of course, you still need to securely install any certificates and keys on your device, and you need to do that in a secure environment where nobody can get in and listen to what you're doing. And all of these things requires a trusted provider, so that in the end, everybody is happy with the fact that your certificates have been validated, and they know that they're speaking to you and you're speaking to other people, and so on. So to conclude, I'm just running into my question time, but I'll just conclude briefly. Wireless IoT devices present particular challenges with respect to security because they are rather limited and they're rather open in terms of connectivity. New generation devices, I've shown you a couple of new generation devices, offer better support at a price. If you're considering an IoT system, then you should certainly consider what level of security, if any, you need when you start the design of your system, not just of the devices, but also of how you connect your devices to the rest of the world. I don't believe there's any right or enough or wrong solution to this equation. The balance has to be made, and you have to look at the cost, the risks, and the consequences. Gradually, the number of tools that exist out there to help you are improving, but you still need to do a lot of DIY work, I beg your pardon, yourself. Thank you for listening. If you have any questions, I'll be more than happy to respond. I was hoping that one of my colleagues would have come on with a question or two, but I haven't seen them. I should have thought of a question for myself. I'll try and think of a question, a sensible question. I suppose the question is, what might be the difference in cost between the different options I've presented in terms of the end device? If you look at the three devices I presented, the 1507, 2053, and the 1907, you're typically on a scale of adding, each time you go from one to the next, adding maybe 25 to 30% of the initial cost. So if you consider that you're starting off at between $4 and $5, then you end up with the 1507, then you probably move up to $6 to $8 for the 2053 and closer to $10 for the device with a secure element. Particularly considering with the secure element, you're going to need to have a way of programming the secure element securely before you start, which is a part of the cost of the whole operation. Another question you might ask is, if you're trying to connect to one of these cloud-based servers, how do you manage certificate conundrum? I can answer for one of them, because we've been involved in working with Google Cloud. And Google Cloud normally has a whole range of trusted root certificates that they provide for people that are connecting from a PC or a phone. And that doesn't present a problem for the PC or the phone, because when you have a PC or a phone, the root certificates of all the trusted root providers are already on those devices. Unfortunately for the IoT device, as I said earlier, you're limited in memory and you're limited in the number of certificates due to that you could put onto the device. So there's no way you could store all the certificates of all the trusted root providers that Google uses on your device. So fortunately, Google, and I guess Amazon and the other and Azure have all thought about this. Google in particular has a special connection link. Rather than using the standard Google link, there you have another Google link where you have just 2 certificates to store. So the cloud server providers have thought about this problem with regard to providing certificates and controlling the authentication, certification, encryption process. But you still have to do it yourself. In other words, part of the commissioning process of your end node includes somehow writing certificates into your device. You may also need to write local certificates. If it's a Wi-Fi connection, you will need to maybe add certificates for the enterprise Wi-Fi connection to your device. And all these aspects in small IoT devices are potentially much more problematical than they are in a bigger phone-based system or PC-based system. I can't think of any other questions to answer you just off the top of my head, but I hope you've enjoyed this short introduction to wireless IoT security, and I hope that you'll be able to understand how you might want to prevent your system being attacked in the future, and how you need to start from the ground up and not just think about bolting on security when you've finished your complete system design. And as I said earlier, there are quite a lot of devices now out there which have enough security for the typical IoT wireless system. And I think I'll stop there because I'm just wobbling on. Thank you for your time. And if there are any further questions, you can always contact me directly on my email address. I'd also like to thank the team at Inside SiP for helping me on this, and in particular Nick Wood, who wrote an article from which this presentation was based. Unfortunately, Nick couldn't do the talk himself because he was in transit from Canada. Thank you. Have a good day. Bye-bye.